Welcome back to our Fleet Assignment Model lecture. In this video, we'll discuss how to use this model to help us design our timetable. We'll first discuss the complexity of designing an airline timetable, and then we'll discuss a couple of adaptations to the traditional Fleet Assignment model to support our timetable design decisions. Well, in fact, it is almost never the case that an airline wants to develop its timetable from scratch. When discussing the timetable design problem, we are commonly talking about incremental or marginal changes to an existing timetable. But why is that? Why does the timetable design usually follows an incremental approach? Well, there are multiple reasons for this. The first one being that to design a new timetable from scratch requires good quality data, eventually referring to demand per hour and variations of demand between days of the week. This data is very hard, if not impossible to get. The airlines maybe just have detailed hour information from the times that they are flying or potentially from the times that their competitors are flying in the same market. A void of knowledge exists in the periods outside these flight hours. So strong assumptions will have to be followed, and airlines are aware of the risk of such approach. Secondly, to compute a full new schedule, considering the implications of the timetable on the crew and aircraft schedules, is a hard problem to solve, requiring much investment to set it up and to run it. In parallel with this, there are also all the considerations that will have to be done in terms of the airport constraints, such as the slots or maximum number of gates or stands available. Ultimately, the airline will have to reinvest in their infrastructure at each airport, changing, for instance, the number of check-in counters, the personnel located in each airport, change the ground service and aircraft maintenance contracts at different airports, etc., if the solution obtained is considerably different from the solution that they are running at that moment. And finally, airlines develop some fidelity bounds with some of their passengers in terms of time they fly to some of their destinations. This is a particular case for business passengers, which tend to rely on a fixed schedule to fly some of the routes they commonly fly. So airlines do not necessarily want to change their timetable from scratch. So what airlines tend to do is just to adapt their schedule from previous years, considering a few potential changes to their schedule. By following such approach, the airline can still eventually use their historical booking data, because demand should not change much. Furthermore, no major investments will be needed at any airport, and slot changes could be, in principle, renegotiated. Finally, there is the fact that the timetable consistency can still be maintained. We'll discuss two possible approaches depending on the goal from the airline. In the first approach, we assume that the airline only wants to redefine the departure times of a set of flights, while in the second case, we'll consider the option of adding or removing flights to a previous timetable. For the first case, in which we just want to consider a change to the time of some of our flights, we can create multiple replications of these flights under consideration, each one separated a few minutes from each other. The flights that we are questioning their departure times will be clustered in a set called LO. In our graphical example, these are flights J and M. The replication of these flights, so all these flight arcs around flight J and flight M, are clustered in a set LOI, that is the set of optional flights for flight I. We can also have flights in our schedule which we want to guarantee a fixed departure time, or in other words, that we do not want to consider a change to their departure times. These flights will be clustered in the set LF, and in our graphical example, this is flight L. Note for the flights with optional departure times, the idea is that we will only select one of these flight arcs. So we can adapt our model to consider these options. The only change that we need to introduce is to divide constraint C1 into two sets. In our traditional fleet assignment model, we only have the constraint C1F applied to all flights in our timetable. That was to guarantee that we will have to allocate one aircraft type to each flight arc and only one aircraft type. In the new model, we have these constraints only applied to the flights that have a fixed departure time. To the other ones, to the ones that we consider different options for the departure time, we do have constraint C10. This enforces that only one of the options for each flight I in our set LO will have a value equal to 1 in one and only one of the time-space networks of the fleet types that we are considering. This is guaranteed by summing over the set LIO and over our fleet types K. Note that in this case we are assuming that these time changes are small, that the disruptions to the passenger itineraries can be neglected. This is not the case for case 2. In case 2, we look into the case that we want to consider adding and removing flights to our timetable. To discuss this case, I'm suggesting to follow the approach proposed by Lohata-Panon and Barnard in 2004. In this approach, they divided the flights from the base schedule into a mandatory list of flights and a list of flights that can be deleted. Then they added a list of potential new flights. These new flights were added to the flights that can be deleted and they put it together in an optional flight list. The final list of flights to consider in our model is then the combination of the mandatory flights and these optional flights that we created. Following this logic, we need to extend our notation. So we do need to have the sets mentioned before, that is the set of mandatory and the set of optional flights. In addition, we need to model the passenger itineraries because they are affected by the addition or removal of our flights. So we consider now the set P of all itineraries in our portfolio and PO as a set of itineraries which contain flights that are in our optional flight list. To capture this link between flights and itineraries, we also had a set of flights included in each itinerary queue. For parameters, we need to provide information regarding the number of flights that are part of each itinerary. Finally, we'll have the decision variables ZQ, which are binary variables that define if the itinerary is included in the timetable or not, given the flights that we may end up adding or removing from our timetable. And this is the final model, integrating the fleet assignment model with the passenger mix flow model and the option to add or remove flights from a list, considering the impact on the passenger itineraries. Within the blue rectangles, we do have the difference to our standard itinerary-based fleet assignment model discussed in the previous video. The first change is the objective function. We have a new term now that is a fare that we lose if itinerary Q from the set of itineraries containing optional flights ends up being unfeasible, being removed from our portfolio of itineraries. We have again the split of constraint 1 into two subsets of constraints. The first constraint C1F referring to the mandatory set of flights and the second C10 referring to the optional set of flights. To the latter, since we may define not to operate all optional flights, we have the sum of the flight arc decision variables to be lower or equal than 1. Finally, we do have two additional sets of constraints, C6 and C7. These are constraints that control if the itineraries are still possible, given the changes introduced to the timetable. The first set of constraints checks if for all flights included in itinerary Q, there is an aircraft type being allocated, that is, if the flight will be considered in the timetable. If any of these flights does not have an aircraft type allocated, the ZQ variable has to be lower or equal to 0, or in other words, the itinerary Q has to be removed from our portfolio of feasible itineraries. Constraint C7 do a similar check, but, let's say, in the opposite direction. So we are checking if we do have all flights needed to complete the itinerary as part of our list of flights included in our final timetable. If the number of flights covered by any of the flight types in our poem is equal to the number of flights that should compose the itinerary Q, then we can consider this itinerary Q into our portfolio of feasible itineraries. And with this model, I'd like to conclude our lecture on the timetable design and fleet assignment problem. Let me know if you have questions in our Q&A session or in the comments below. I'll see you in the next lecture. Bye-bye.